Hi, my name is Travis Humes.
I'm Jenny Phillips.
Carl Shorey.
Ijama Onyechukwu. Yolanda Watt.
I'm Jorge Matute.
I'm Alex.
And we're presenting on the E2.
We'll be doing E2. So, E2 reaction is a one-step mechanism that involves two substituents. The name E2 derives from the fact that it's a bimolecular reaction. During the 1920s, Sir Christopher Ingle proposes a model to explain E2 reaction. The model he proposes involves a carbon-hydrogen and a carbon-halogen bond breaking to form a carbon
reaction. A proton is removed in order to form a double bond. And usually E2 reactions are, most of them deal with tertiary or secondary alkyl halides. However, there are some cases where E2 reactions deal with primary halides, and which this reaction occurs is second order kinetics because there is a starting group or the alkyl halide involved as well as a very strong base. It's two things. At the same time, we need a great leaving group on the alkyl halide so that it can leave once a hydrogen is deprotonated to form a double bond or pi bond. And so the starting material is usually sp3 hybridization, and the end product will be sp2 hybridization for our double bond.
This here is a coordinate reaction, just showing the energy profile of our E2 reaction. And basically here we see that the base is unstable, just ready to react with something. The starting materials at a higher energy than our product, but the highest actually is the transition state. And so this base is looking for something that's going to make it stable, if you will, if you dare say. And so it's going to grab this hydrogen by all means. It's going to take some energy to grab this hydrogen. However, when the hydrogen is removed, the electrons are transferred and the leaving group leaves. We have an even lower energy profile for our alkene, our base attached to the hydrogen, and our leaving.
We're talking about stereochemistry involving an E2 reaction. A strong base is generally required, one that would allow for displacement of a polar leaving group. The stereochemistry of the hydrogen to be removed must be anti so that the leaving group, the pair of electrons from the breaking of the CH bond, denotes into the anti-bonding orbital of the C bond leaving to its loss as a leaving group. So for example, we have OH as a strong base and it has two unstable electrons that's going to attack the hydrogen. The hydrogen is then going to form a double bond between these two carbons. The electron is going to flow along and eventually go to Br, causing the Br to become the leaving group. So for this reaction now, we're going to form a double bond from here, and then the molecules are going to spread out because there's less steric between them. So that will be the completed reaction.
For an E2 elimination reaction, you need a strong bulky base with a tertiary alkyl halide. An E2 reaction is an exothermic reaction and is a one-step single process. For a E2 reaction, the most favored is a tertiary alkyl halide. The second favorite is a secondary alkyl halide, and the least favorite and least likely to happen is a primary alkyl halide. An example of a base, a nucleophile that reacts with in an ether reaction is a third butyl oxide. Okay, so now I'm gonna show in some examples that I have the teacher showed. So here I have a double bond an oxygen that this will react with this right here, and so I have basically I have this oxygen will attack will react with his base right here. It will attack one of the hydrogens right here. I will attach to that, and hydrogen would double bond with this chloride, would double bond. So the final step, you have a hydrogen attached to the oxygen and double bond of the chlorine. And that's basically what I have to show you. And thanks for watching.
So if we would use this flipped ring here as an example and maybe add a bulky base, like it's a bulky base because it has so many carbons, and we could use maybe methanol as a solvent. What we will get is, we know sodium has a full positive charge, so oxygen will have a full negative. We have the oxygen here attacking the hydrogen. The hydrogen then breaks off, comes here, and then from here to here. And what we will get now is we'll have a double bond forming right here, plus the bromine, which is now
So generally when people speak of E2 reactions, they classify it as a removal of a halogen, which could be chlorine, fluorine, bromine, from a carbon molecule along with a hydrogen atom. But you can have other leaving groups made apart from the classical ones that everyone talks about. And an example of how you do this would be the preparation of bromobutane. One bromobutane from butanol using substitution under acidic conditions would be done for an overall E2 reaction. Sulfuric acid is used to pronate the weakly and basic hydroxyl group so that it can be converted into a good leaving group. This allows for the hydroxyl group to leave as water. There will also be a side reaction which occurs, which is the formation of hydrogen bromine from the reaction of sodium bromide and sulfuric acid, which is used to pronate the weak hydroxyl group. So it turns into a good leaving group, basically.
So far what we've covered about the E2 mechanism is that it is primary or secondary. It is a bimolecular, and another important factor about E2 is what we've already seen, the basic stereochemistry of moving the beta hydrogen into a double bond. Now what makes E2 so special is that if we were to take E1 for example, right, E1 would just need a substrate, meaning if it has a tertiary it can still function as an E1, but in E2 what we need is a substrate and a very, very strong base, because we need that base for the displacement of the leaving group to happen, just because this is a bimolecular step. But it would take a little more complicated into a more applied theory into, let's just say, a cyclohexane. Now a cyclohexane, for it to go through an E2 mechanism into a major product, you can't do it the same way as you would do with a regular stereochemistry of E2. You would have to do chair conformations. Now, in doing chair conformation, it is very important to note that the leaving group must be completely opposite to the hydrogen. So it must be anti-hydrogen to the leaving group, because the anti-hydrogen is going to be the double bond. We can't have the same anti-hydrogen and the same leaving group on the same side, because then it would be a double bond on two carbons at the same
So if
time.
you can't really see, this is a cyclohexane right here. If you can't really see, that's a bromine. Okay, that's a bromine, and these are basically your methyl groups attached. Now, for an E2, right, an E2 reaction to happen, you cannot just add a hydrogen and work its way to a double bond. It will not work like that. You will need to do chair conformations for it to be successful. Now, this is the bromine. This is a good leaving group, so this will most likely leave. But the most important thing is, as I mentioned before, is about the anti-hydrogen. Now, this hydrogen will not be the anti-hydrogen because it is on the same side. This is why exactly this will be the anti-hydrogen because it is the complete opposite of bromine. So this bromine will leave, and this will happen to be as a double bond. This is a basic product from what I was talking about with the bromine leaving group. So this is basically chair conformation that's right before we make into the major product. So it's already double bond, and that's the hydrogen that we were not supposed to use for the double bond. If you can't see, I think there's something wrong with the lighting for some reason. So this is basically, this is the methyl group, this is the methyl group, this is the hydrogen, if you can't see. This major thing is a double bond that was formed just because we use the anti-hydrogen. Now, if we didn't use the anti-hydrogen, this double bond would have came here, which, like, again, violates everything, violates all the factors. So this is the main product, this is the major product. The double bond is here, and let me erase that right there. So the double bond is right next to methyl, and the hydrogen on the opposite side, which is why it's a successful E2 mechanism.